This one, this is the Dalton's law of partial pressures. In a mixture of gases, each gas exerts its own pressure, a specific pressure. The sum of those specific pressures is the total pressure. Gases, yes, gases. The total pressure is the sum of the specific gas pressures. In formula form, pressure total is equal to the sum of all the individual pressures from the individual number 1, say, up to however many gases you have, which simply means if you have multiple gases, 1, P2, plus all the way up to P sub n, you just add them together. It's a real simple concept. It looks kind of nasty right there, but it boils down to, say you're given a mixture of gases as follows. Put this up a little bit. CO2 has a partial pressure, CO2. This is, you take a P, capital P, and put a subscript of the gas on it, and that's called partial pressure. And let's say that's 175 millimeters of pressure. Then you have O2, and the same pressure of O2 is equal to 281 millimeters. And then you have some neon gas in there, and the pressure of the neon gas is 195 millimeters, and the remaining portion of it is water vapor. Okay, what's the pressure of the water vapor? Right here. If that's all that's given, you assume pressure total is equal to 1 atmosphere. If that's all that's given. If they don't tell you what the total pressure is, then you assume 1 atmosphere, which is 760 millimeters of pressure. From the formula, all we have to do, pressure total is equal to pressure. Total pressure is CO2, O2, neon, and water. Okay. CO2 plus pressure of O2 plus pressure of neon plus pressure of H2O. Now we got it straight. Thank you, sir. Okay, so with 760 millimeters over here, they're all in millimeters. Okay, CO2 was 175, O2 is 281, neon's 195, and then the unknown is the water. So now we solve for, let me make that look a little bit neater, H2O. And so we take the water and on one side and subtract these from the other, and we have pressure of H2O to equal 760 minus 175 minus 281 minus 195 millimeters. Okay? Here we go. I I get 109. Anybody back me up? Okay, 109 millimeters. That's all we wanted to do in that. So, summarizing this is all this. So the problem data is simply going to be partial pressures. And or a total pressure. That's all you're going to have to deal with in here. And you apply it to total pressure is equal to P1 plus P2 plus however many individual pressures you have. Anybody get it? It's really not that difficult on this. Well, the stuff we just finished was light years ahead of this. Let's move this out of the way. There are two terms here that I want you to be aware of. Now let's start effusion and diffusion. I don't think it has two F's. U-S, no, it does. U-S-I-O-N. Diffusion. We'll start with diffusion. Diffusion is the migration of gas particles at random through a volume in which it's contained. So it's like I open a bottle of perfume in the front of the room. After a period of time, people in the back of the room are going to smell it, so to speak. That's diffusion. And this is the migration of particles by random motion. In liquid terminology, when we talk about properties of liquids, and say you take a drop of food color, and I know everybody's seen this before, when you put a drop of food color in water, you'll see it spread out slowly. And eventually it'll fill up the whole glass of water in that color. That's a Brownian movement is what it's called. Now, that terminology is not used in the gas issue, and per se, say it diffuses. But that, in essence, is the random motion of a particle under the energy it contains from around the container it's in. Now, effusion is the discharge of a gas out of a small opening. Say from a cylinder. If you have, for example, a container, say with gas in here, and you puncture it, boop, knock a hole in it, you can visualize that, then you're going to have a rapid discharge of the gas, and that is the effusion process. And the relationship and problems that you need to be aware of is the gas right there. So for Graham's law, states that the velocity, the effusion velocity is inversely proportional to the square root of the mass of the particle undergoing effusion. molecular weight, not mass, mole weight. Sorry about that. I always think in terms of size, mass, but it's actually mole weight of the particle being discharged. So this comes out like a velocity, v, of effusion of particle I, X, Y, Z, whatever, is proportional to 1 over the square root of the mole weight. That's all it boils down to. So this, like the empirical gas laws we did earlier, sets up a before and after issue, a relationship, and turns out to be a comparative so that you can compare effusion rates of different particles. Okay, so this is what you'll ultimately use. Now that's Graham's law. Questions will come, what is Graham's law? Which of the following describes Graham's law? And you talk about the velocity inversely proportional to square root of molecular weight. But when it comes to doing numerical problems, it's a comparative between particle sizes. So you are dealing with particle sizes primarily. Now, the velocity that the stuff's coming out is 1 over the square root of the molecular weight, and proportional. And to make this an equation, you take velocity is equal to k onto 1 over the square root of molecular weight, like that. And again, you're comparing particles. So the k for particle 1 is equal to k for particle 2. And so k is what you're looking for in terms of velocity times the square root of molecular weight. Now, let me show you how it comes together. Compare effusion rates of, CO2 gas versus SO2 gas, sulfur dioxide, under equivalent conditions. Now, get that now, I'll wait on you. Okay, this is the issue right here that you want to concentrate on right now. So we have a K for the CO2 and a K for the SO2. These are equal. They're constants. So the effusion constants are assumed to be equal. Well, if that's true, then the velocity times the molecular weight, velocity times the square root of molecular weight of CO2 is equal to the velocity times the square root of molecular weight of SO2. Like that. We can write this equation in terms of CO2 velocity, or we can write it in terms of SO2 velocity. So I'm going to start with it depending on the problem. The problem may ask you for CO2, or it may ask you for SO2. Okay, and I'll show you how it comes out. This one is the velocity of CO2. Well, if the velocity of CO2 is equal to the velocity of SO2 times the square root of, and I call molecular weight of SO2 under the radical, divided by the square root of the molecular weight of CO2. Okay? Or you will have the velocity of SO2 written out and the velocity of CO2, square root of molecular weight of CO2, divided by the square root of the molecular weight of SO2. It depends on how the problem comes to you in both ways. Now, here's what we're ultimately getting to. Okay, VCO2 is equal to velocity of SO2 times the square root of 32, and 32 is 64. That's the mole weight of SO2. And CO2, 16, 16, 32, 42, 44, square root. Okay, that's the mole weights of those two. The velocity of SO2 is equal to the velocity of CO2 times the square root of 44 over just a reciprocal, 44 over 64. So a comparative is this. I'll show you. That's 9 divided by 6. Let's get 44 square root reciprocal times 9 equals 1.36. This one, CO2, velocity of SO2 times 1.36. I think the reciprocal. And velocity of SO2 is equal to velocity of CO2, whatever it may be. And I'll show you an equation for that. 0.73. Now, this is what it means. Okay? All right, Okay, CO2 is 1.36 times faster. That's what that means than this one. And that's what one of the problems might ask you. And CO2. On the other side is just opposite. Velocity of SO2 is only 0.73 of velocity of CO2. It's only a fraction of the speed of CO2. CO2 is a smaller particle. Right here. Smaller particle. The problems will say, given SO2 compared to CO2, which one's going faster, diffusion faster, and how much? Okay, and you have to go through this. Of course, you've got to calculate your formula weights and calculate your two relative velocities in that context. Time of diffusion. Given, I'm going to use SO2 is 64 atomic mass units, and CO2 is 44 atomic mass units. Okay, we're going to run a race. Here's the finish line. Both have the same amount of energy. Which one's going to get there the quickest? The lighter one. They're both under the same conditions of pressure, and they're going to spit out of this amorphous, okay? They're under the same conditions. Which one goes faster? It's the lighter particle. It's a truck, a big car versus a big truck. They both start under the same conditions, but the little particle is going to go way faster by 0.136 times faster than the heavier particle. So the time it takes for the CO2 to get there versus the time it takes for the SO2 is what? This is shorter time than this one. That is, the time of CO2 is less than the time of SO2 to go from wherever it is to across the finish line. That changes the formula into a reciprocal. And you take velocity of, say, 1 times the square root of molecular weight 1 is equal to the velocity 2 and the square root of molecular weight 2, whatever that you're using, whatever 2. And instead of using V, you'll use T, but it's an inverse. In physics, velocity equals rate times the time. Distance equals velocity times time. Right. I have to write it down. And velocity equals distance over time. So it's inverse. And it's all coming out of the same cylinder. And the wall thickness is the same all the time. D becomes 1, and you just plug in the velocity there. You have 1, you have a formula, square root of M1 over T1 equals square root of M2 over T2. Okay, problem is, say you're given N2 gas effuses from a cylinder in 35 seconds. How long will it take for effusion of oxygen gas under same conditions. You've got three of the unknowns. You've got three of the variables and one unknown in here. If whoever you assign the T to, how long does it take? You have to associate that with the mass. So using square root of, say we're using oxygen and nitrogen, we want to go N2 over the time of diffusion for N2 is equal to the square root of O2 over the square root of O2. So we simply have, come up here. Okay, the square root of the mass of N2, 14 is 28, square root of 28, yep, is I'll just go 5.29, and the square root of mass of O2, 32, is equal to 5.66. Okay. You just plug it in. Oh, and we're given the effusion for nitrogen is 35 seconds. Okay, I'm going to lose the problem here for a second. Okay, so nitrogen is 5.29 divided by 35 seconds, and this is grams per mole. The grams per mole is going to cancel out anyway. And then we have oxygen is 5.66 and T of O2. Now just double checking. And simply put, the time for effusion of the oxygen is multiply both sides by T and then divide both sides by that ratio, and it inverts and multiplies. So we have 5.66 times 35 seconds divided by 5.29, and you get 5.66 times 35 equals divided by 5.29 seconds. I got 37.4 or 37 seconds. Well, only takes 2 seconds longer. I'd probably give you a compound. I just chose those off the cuff, but probably give you two compounds that are radically different in mass in terms of that. I only need to cover the kinetic molecular theory, and we'll be out of this and go into. I didn't figure I'd